Hello everyone, my name is VanDomelen. I'm a PhD student at Portland State University, and I'm going to be talking to you about freer arrows. So, for a little bit of context, let's say that I am in a situation where I want to write a program with effects, and I decide I want to create an embedded, domain-specific language, and I know the kinds of effects that I want to include. I can encode my effect something like this, where I have two different events, one for reading an integer from somewhere, and one for taking an integer and writing it. I'm going to be calling the data structures like read-write effects, and these two constructors, read and write, are the events in the effect. This is the format that you would use if you wanted to put an effect in a freer monad, which is defined like this, or this is one of the implementations of freer monads. We have two constructors that roughly correspond to the return and bind operations from the monad type class. One thing to note, though, is that in bind, we always start with an effect. It's e of x. Do I have all these? Yeah, e of x. And we continue with this function that takes in an x as an input. So if I wanted to write a program using this read-write effect, I could use the bind constructor, bind the output of reading an integer to a variable x, and then write using that same x, and then return, say, a unit. I could also write in do notation, which is probably the more common way to write that, but we need something to embed the effect into the freer monad. So embed is a nice way to do that. We have some advantages in writing our code this way. It's simple to set up. We just need to define the effect, and we can plug it into the freer monad. We get a sequence of events represented syntactically with the constructors for bind and return. And we can run this in another monad by interpreting our effect into that other monad. We could even give multiple interpretations into different monads or into the same monad. Very flexible. So what's missing? We have a challenge with static analysis. If we look again at this bind constructor, the continuation takes in the type of the output of the effect. So we need to have a value of that type to be able to know what event's going to come next. So we can't inspect inside the continuation without running that function, without having an object of that type. So if we wanted to do static analysis on this, we either have to run the whole computation, or our static analyzer can't be a Haskell function. So our solution that we propose is freer arrows. I just gave you a little bit of background on freer monads. I'm going to continue with the brief introduction to freer arrows, and a little bit of explanation on why we think that freer arrows can be useful. So, starting with an introduction, we make some contributions in our paper. We propose the freer arrows data structure for writing embedded domain-specific languages in Haskell, and we study how they can be used and explore different implementations and interfaces that you can use to interact with them. So, let's take a look at another version of this read-write effect. This time, there are two type parameters, one representing the input type and the output type. And our read event now takes in a unit and outputs an int, and our write takes in an int and outputs a unit. We can use it in our freer arrow data structure, whose implementation I have here. And you don't need to understand this all at once. I'm going to explain the parts that are relevant. So just like freer monads give you a monad instance for free with your effect data type, the freer arrow is going to give you an arrow instance for free. If you're not familiar with arrows, the simplest example of an arrow is the function arrow. And the constructors of freer arrow resemble some of the arrow type class functions. In particular, ARR lifts a pure function into the arrow, and we have composition from the category type class. These are represented by these constructors. Hom, we lift a pure function into the arrow, And composition, we take a pure function, and I'll explain why this looks this way in a little bit, and an effect that goes from A to B. And this third argument acts as a continuation for how to continue on with the computation. And we package it all up into a Fourier arrow from some type X to some type Y. So looking at this composition constructor, our first argument is a pure computation which returns a pair. So it's kind of doing two things. We can do whatever we want to the input as long as at the end we package it up into a pair. And the reason we do this is that the effect takes in an A as an input, and sometimes we want to have a part of the part of the input that doesn't run through the effect. So we separate it into a part A, which runs through the effect, and a part C, which kind of passes it by. Then, for our third argument, it's like a continuation, but it's another object of the type Fourier arrow. So we'll see another constructor that we can potentially match on. The input to the continuation is both a pair B, which got transformed from the A, and a C, which was left untouched. Yeah, so Fourier arrows, like Fourier monads, can be run by interpretation, but we interpret it into another arrow instead of a monad. This ends up being really easy because any monad has a trivial arrow that we can derive from it, the Kleisli arrow. And so we can still interpret it into a monad like IO, which we'll need to do if we want to have the ability to use the IO monad. Then we can write some functions in a similar way as before. Here I'm writing it out with constructors again. One of the caveats is that we do need to still take our input and turn it into a pair. So this is going to look really messy at first. So we'll compose the read event into the write event. We don't need to do anything with the input going to the write event because we already got the input on the left side of the pair from read. And then at the end, if we want to return unit, we can use the hom constructor to finish with a pure computation. Yeah. This ends up being like a list of events, which will run in order, ending with a pure computation. The pure computations happen before every effect, so we kind of get an alternation between the pure and impure computations. And there are a couple different ways to write this because this is really messy. We can use the category notation with the forward composition operator. You could also use the regular composition operator if you're more comfortable. And we have another version of this embed function, but for arrows. You could also write it with the arrow do notation, which is a little bit more explicit about where the data flows in the notations. We have to explicitly say which things in the environment pass into each event. So it looks a little noisier than the monad version, but it's doing roughly the same thing. Okay, so now I'm going to talk about what Fourier arrows can be used for. And the first thing we're going to focus on is static analysis. So what kind of static analysis can we do? We can write simple recursive functions on the structure of the Fourier arrow. For example, if we wanted a function that could count the number of events, we could write that simply with a recursive function. We know that there are going to be no events in the pure part that ends in the hom constructor. And then each comp constructor represents one event. This is just representative of the kind of pure functions you can write. We're probably not usually going to want to be just counting events. We could also have functions that modify the computation. So we could have a function that takes a Fourier arrow as an input and outputs another Fourier arrow, maybe with some domain-specific optimizations. We'll talk about that a little bit more later. One thing that we were able to do, which was really fun, is summarize the events in a monoid. So if you have a function which can kind of take a event and for any input and output type, convert it into an object in a monoid, then we can collect all of the events into that monoid. So for example, you could collect them all into a list and get a list of all the events that will happen. But I have to comment on expressiveness. There is a cost to all of this. Freer arrows trade off their expressiveness for static and analyzability, because the more an abstraction does, the less we know about it. Freer monads had the flexibility of that continuation where, based on the output of any event, we could decide later on what the next event or the next computation that will happen will be. The arrows are more expressive than implicative functors, but less than monads. And in particular, our Freer arrow, like I said, it's like a list of events. And in the version I showed you, each of those events will happen, and they'll happen in order. We do construct two additional variants, one weaker, a Freer pre-arrow, and one more powerful, a Freer choice arrow. A Freer choice arrow is one that I'll talk about later, and it gives us a little bit of ability to have more expressiveness. We can have events that might or might not run. But first, do we have any real examples using Freer arrows? Of course. We did a case study in choreographic programming, and we used the library Haskell for choreographic programming in Haskell. I'll start with a little bit of a summary of Haskell so that we can understand kind of the language that we're talking about. In choreographic programming, we have a computation that's going to be running on multiple machines or multiple participants. I'm going to be calling them endpoints, as the library does. And they work together to compute something. So the great thing about choreographic programming is that the program is written once for all of the endpoints, and it's executed differently at each one. The original Haskell library is implemented using Freer monads. In particular, we have the choreo monad and the network monad. The choreo monad, it's not super important what the events are. I'll list them here just to get an idea of them. You can do local computation on one endpoint. You can send data back and forth between endpoints. And there's a special event for synchronizing choices between the endpoints so that they're always in sync as we go through the computation. The network monad is the type of programs projected out. So whereas the choreo monad, all the events are from a global perspective, and the network monad, they're from the perspective of just one endpoint, the one that will be running. So similar to the ones in the choreo monad, run has a computation in the underlying monad M, kind of corresponds to local. Send and receive are the two kind of parts of sending data from one endpoint to another. And broadcasting is the way that we implement synchronizing choice. Here's an example choreography, just so you can look at one for a little bit. You don't really have to understand this, but you can see there's Alice and Bob get talked about, and this is a sort of version of the echo example I have earlier, but in this case, Alice is the one to read an input, which gets sent to Bob, and Bob's the one that writes it. In Haskell, the thing that is used to send the computation to each of the endpoints is called endpoint projection. We take an instance of the choreo monad and the location we want to project it to, and then we get the instance of the network monad. Endpoint projection specializes the choreography to one endpoint. And it kind of looks like this, although I'll show you later, this is a little bit of a lie. But if you were to write programs in the network monad representing the ones that get projected, you would have two different versions, like one for Alice and one for Bob, using the network events instead of the choreo events. There's one limitation to endpoint projection in the original Haskell library. The recursive call to endpoint projection is partially applied. So it's dynamic, and it waits for the output of each event to continue projecting the choreography to whichever endpoint is running it. Ideally, the endpoint projection would be static and be able to run fully before starting to run the computation. And separately, the choices must be broadcast to all endpoints, even if they don't need to know about them. Our solution to these problems is also Freer arrows. we replace the freer monads with freer arrows in Haskell', and most of the interface remains largely the same. This was one of the big advantages. We ended up with two versions, one with choice and one without. It turns out that we could probably use the version with choice most of the time. Without choice, though, we don't want to be synchronizing branches because there are none. So we don't need the cond event or the broadcast event from choreo and network, respectively. So using freer arrows, that echo example we wrote earlier would be written like this. Here I've chosen to write it with the arrow type class notation instead of the arrow do notation. But that's not really important. You can use either one of them. And we get one benefit which is called selective broadcasting. So when we do have a program, this is one using the monadic version of Haskell'. Sometimes we have branches, and the cond event here is what synchronizes the branches so that each endpoint can follow along with what to do next. In this example, we have a simple key value store which has three participants: the client, which is going to be using the key value store, the primary endpoint, which is going to be handling, storing the data and giving it back to the client, and then a backup to kind of mirror all of the data on the primary. One thing to notice is that this cond branch uses some data from the primary endpoint, but if you look inside the body, we only see the primary and the backup being referenced. There's no reference to client. Their behavior is exactly the same regardless of which of these branches runs, excuse me. But cond in the original Haskell library ends up broadcasting to client even though they're not involved in that part of the choreography. With our arrow version, we can write functions like this participants function, which can actually inspect the body of a cond branch and see which endpoints are actually involved in that branch. Then during endpoint projection, we can use this function and have broadcasts that only broadcast to the parties that need to know about the branch. So in the key value store example, the client doesn't need to see what branch is taken. We can just broadcast that choice to the backup from the primary. It's a little cut off at the bottom. Yeah, so with Haskell using freer arrows, we get a few main benefits. One is that endpoint projection is static in the sense that it can run fully before we start running the program. Of course, everything I'm talking about here is technically still happening at runtime because we're not using any kind of staged programming or metaprogramming. But we don't have that effect where we're alternating projecting the choreography and running it on one of the endpoints. We could imagine two stages, even if they're both happening at runtime. We also get selective broadcasting, like I just talked about. The cond events can be translated during endpoint projection to only broadcast to the parties that need it. We could do static profiling if we wanted to. We can, without needing to run examples of the choreographies, we could construct them and then inspect them to see how many events are running. If we project them to the endpoints, we can see how many sends and receives or local computations happen on each one without ever needing to simulate it. We could also do some kinds of optimizations. We experimented with one of them where we take two sends that happen between the same two locations and we could combine them. So maybe in a setting where you wanted to reduce the number of times you communicate over the network, that would be potentially a useful optimization. Yeah, so in conclusion, freer arrows seem to be useful for writing embedded domain-specific languages for effective computations. They do trade off expressiveness for static analysis. You can do operations similar to what can be performed in an abstract syntax tree. One note on that is that it's not an abstract syntax tree. The version that we propose is normalizing, so the events are in kind of a list more than a tree. They have an interface similar to Fourier monads, and you can sometimes use them as a nearly drop-in replacement. And you can use Haskell functions for static analysis instead of needing any metaprogramming or GHC plugins or anything like that. So we have more in the paper. Feel free to scan the QR code, read our paper. There's some cool things in there, and if you look in the appendix is separate, but there's some cool things in there as well. We're working on some future work. We'd like to explore more variants of the Fourier arrows and see if we can get like a single version, but feel free to talk to me after the talk if you want to. Yeah, thank you.
Any questions?
So I have two questions. One is more concrete and one more open-ended. So the concrete one is, do you have any examples of Haskell programs that cannot be rewritten in the arrow style?
Well, I mean, out of the examples in the Haskell repository, I think we found that several of them couldn't, because a lot of them use recursion or iteration to do something, and that's not supported by the Fourier arrow data structure by itself. We do have a note in our paper that you can combine it with another data structure, for example, for iteration. We were able to come back from that, but we don't have any, like we didn't call out any specific examples of programs we can't write.
Right. Well, I meant more like more really where it can't possibly be made to. Yeah. Okay. So my other question was, oh shit, what was my other question? Maybe. Oh yes. So in the arrow type class, there are situations where it's not good that the R method is in the arrow type class because it means that you can't interpret. Like you can't use arrows to write things that you want to interpret as something other than a Haskell function. Mm-hmm. And it seems that this Fourier monad construction bakes in more pure functions everywhere, mainly to do the first, second thing, right?
Yes.
So okay. So do you have any does this approach give you any road towards if there was an arrow type class that didn't have R as a method, could this be still applied, or would you still end up with these pure functions just to do the packing?
Yeah, this is something that we were exploring as ways to mitigate what you were talking about. It didn't end up making it into the paper, but we were looking at ways to maybe do some defunctionalization to get a little bit of better ability to analyze those pure functions as well. I'd be happy to talk about that offline if you'd like, but yeah, we have some future work that we're looking at that.
Thanks.
Yeah.
Nice talk. I really like Haskell as a way, people implement various choreographic languages and they're not widely used. You should implement your own language. So doing it as a library, I think, is a fantastic idea. One comment and one question. So the comment is just point out, John Hughes originally invented arrows in order to do some static analysis of parsing. So this is right in line with the original reason for arrows. So the reason here for using an arrow is not to be able to, you said, I want to do static analysis, but presumably the reason for doing static analysis is it makes things run faster?
I'm not very familiar with benchmarking Haskell. We did try to do a little bit of that. We think that it would make things run faster because we're, expecting that certain static parts get, evaluated once instead of multiple times. Mm-hmm. We had some benchmarks that maybe showed that, but compared to monads, we weren't really sure. It seemed like monads were winning out in kind of mysterious ways.
Is there any other reason for doing static analysis rather than to make things run faster?
Well, I mean, we're hoping that there's some applications in program verification as well. That's the kind of topic that I'm most interested in. We haven't looked very much into that, but yeah, we're hoping that we can do stuff in that kind of realm.
You don't need the static analysis to do the projection part. That's fundamental. You do.
Or,
That's a better answer to Bill's question.
sorry, can you repeat that? Sorry.
Don't you need to do a static analysis to do the projection part?
No, they don't.
Yeah, the original Haskell library does endpoint projection without doing the static analysis. But it does it, like I said, alternating at runtime with the running the projected program.
So there really should be some graphs in this paper to show it goes faster. And if they're not, then your conclusion is, here, we thought we had arrows, we thought they'd make things better, but of course they're less expressive than monads. Turns out monads run just as fast, so don't bother with arrows. That's a perfectly reasonable conclusion, if it's true. I don't know.
Yeah, we'll have to look into that.
If there's, oh, go ahead. Okay, so no, there are not any graphs in this paper. We had a different paper at PLDI earlier this year that had another mechanism for making Haskell's broadcast more efficient, but not like this. Instead, it required programmer-added annotations to say who was participating in a conditional. And we do have some empirical results that said that that made things faster because there was less message traffic. So in principle, we should get good results like that from this too, but I don't actually have that data.
Have you, is this on?
Yeah.
Yep. Have you considered freer applicatives rather than freer arrows?
Yes, we have. And actually, that's one of the reasons that we use this echo example is this is one that we cannot write using applicatives or freer applicatives. And I think I made a note here somewhere that arrows sit between monads and applicatives in expressiveness.
He wrote that paper.
Oh, yes. Oh, yeah, hello. But yeah, but we did start, that was where we started, is we were exploring applicatives, found out that we couldn't do what we wanted to, and then discovered arrows as an alternative.
Is there, I mean, is there anything useful to be done with applicatives, or is it just too impoverished?
I mean, I think there were definitely good results with applicatives. I mean, I think, yeah. What was that? The echo example, yeah. Let's see if I can find. I'll show this version. I know there have been good applications in parsing.
No, I mean, in your application area.
Yeah, I'm not really sure. Like I said,
Okay.
we made an attempt and it didn't work out, and that's where we discovered arrows. Yeah.
Fair enough.
Thank you.
So I wonder how this approach compared to tracking the effects in the types. Like you can, for example, you can track how many echoes you have sent using typelets, right? So that allows you to do static analysis, and also I think that gives you more control. Like you can more precisely specify what you can do and what you cannot do, right? You can say to transition from this type, like from this state to that state, you have to perform that particular effect. Mm-hmm. So I wonder, like, curious what you think about that.
Yeah, I think that's an interesting approach as well. It kind of looks like stage programming in a sense because the types are resolved at compile time instead of at runtime. But yeah, I think that's another approach that would also work. Yeah.
Okay, sorry, one more question. So you have this hom constructor where you can lift any Haskell function into your freer arrow. Do you find that to compromise your ability to perform static analysis, or is that not something?
Yes, it definitely does. I think these pure functions act as a kind of barrier to that static analysis, especially because a lot of the time it seems like what you want to do with that ARA constructor is like kind of routing for the data. That's why we were looking into some defunctionalization techniques or something like that. But as long as you're using that R function, there's not really much you can do to defunctionalize it without using something else in GHC. Yeah.
Last one. So since you have this slide up,
yes.
Can you just comment a bit on the arrow tax, which is that if you write programs using arrows, you often find that the meaningful part of the program gets submerged in a sea of encrustations of firsts and seconds and plumbing. And the arrow notation in your bottom thing was meant to address that. But I don't feel as if I've got any practical experience about how much of a problem it is and how effectively the proc notation deals with it. I'd just be interested in your practical experience, programming at scale with arrows.
Yeah, we were very hopeful with the proc notation. In that it did simplify that kind of tracking the dependencies of the data flowing through the computation. But what we found was that there were some challenges, especially in that it produced code that was kind of unexpected in certain ways. And this kind of really came out when we were trying to do some of those domain-specific optimizations, because we would expect two events to be next to each other when they really weren't, because
what was it? It desugared into a mass of firsts and seconds, yes.
And one of the big things about that is that it did use that ARR constructor, or not constructor, type class function. And especially in our future work, we were looking at defunctionalization. It basically didn't work at all. We lost all of the benefits of defunctionalization.
So how can we fix this problem that you've discovered?
Yeah, I'm not sure. I'm not very familiar with GHC internals, but we were thinking about looking at specializing the proc do notation so that maybe we could replace that instances of the ARR function calls. It would be really nice if it used first and second whenever possible, because we can at least override what those generate. But like I said, I'm not very familiar with GHC plugins or GHC internals. Yeah.
That's all we have time for questions, but let's thank Grant once again.